We've been talking about conservation of energy, and it just means that and the energy in equals the energy out, or the change in energy is equal to zero. We can say this a lot of different ways. The change in energy of a system is equal to zero, or we can say E in equals E out. We can say conservation of energy in lots of different ways where energy is measured in joules. Well, the Bernoulli's equation, all it is a special case of the conservation of energy. Um, so it's not really, it doesn't have to be called anything different. And it's like the continuity equation. So the continuity equation is just the conservation of energy. Energy in equals energy out. It's just the conservation of energy with a whole bunch of terms crossed out because they're not applicable, because in the continuity equation, we are just looking at the flow, a volumetric flow rate through a pipe. Bernoulli's equation is the same thing, and it's just conservation of energy. It is just E in equals E out. Or if we want to say it, we can say this type of energy plus this type of energy plus this type of energy is equal to the total energy. So if there is more energy here, then there would be less here, for example. So Bernoulli's equation, just like the continuity's equation, doesn't really have to exist separately. It's just conservation of energy. But it is a conservation of energy that has certain assumptions. And those certain assumptions are very useful when we are doing things like sizing systems, sizing pumps, valves, and piping, etc. Because Bernoulli's equation says that there's going to be there's going to be an area. There's going to be an area at one place, and it's going to be different than the area at another place. So in this case, it's gone from a large area to a small area. So the pipe has gotten smaller, it's become smaller. We know from the continuity equation that that's going to increase the velocity. So there's going to be a V2, which is going to be higher than the velocity V1. We also know from our continuity equation that Q in is going to be the same as Q out because we didn't add any flow. Remember that Q equals AV, so that's A2 V2, and Q in will be A1 V1. We know that from the continuity equation. So, but the Bernoulli equation is like the continuity equation, but also, even though in addition to the fact that the area is changing, the height is also changing, the reference height. So the reference height between 1 and 2 actually has a delta H. It has a delta H, where H1 was larger than H2 here. So it is a special case of the conservation of energy in which all of the other terms cross out, except for some of them. And we still have potential energy due to the elevation at H1. So we still have potential energy. So I'm just going to say EP for potential energy. And we still have kinetic energy, E kinetic. And we still have E due to the pressure, just like we had for the continuity equation. And then this is rewritten in the form that potential, kinetic, and pressure in is equal to, it's just like this, E in equals E out. Potential, kinetic, that's our V squared term, pressure, out. And why does it look so strange then? Because we know that potential energy is mgh, and we know that kinetic energy is 1/2 v squared. And where has everything gone? So what has happened is I took the pressure equation, the potential energy equation, and the kinetic energy equation, divided those all by volume, and then that gave me density. Mass density is mass over unit volume, because there was mass in each of these terms. There was mass times unit volume in each of these terms, which is density. So I'll just write that as density. It had density, 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 1, 1, 1. But it's the same fluid that went down to 2. So density, 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 2, 2, 2. But density at 1 is equal to density at 2. And that density came from dividing both sides of the equation, every single term, by velocity. We already had mass from mv 1/2 mv squared, and from our mgh, our potential energy, etc. I divided by volume to get density, and then I crossed out those densities. So this is just a simplified form with densities crossed out because they're the same on each side of the equation. That's the form of Bernoulli's equation that is known and famous. So it is the minimal number of terms possible in the energy equation. And the amount of energies that are changing is we have potential energy here changing into kinetic energy down here. And of course, we have the pressure that is acting upon, that fluid acts upon the rest of the system. And if we say added heat energy halfway through here, let's say we did something like add heat energy, we would be adding Q. Adding Q, then of course we would have to add a Q term, and everything would be different. And it would no longer be called the Bernoulli equation. It would be called the conservation of energy equation. But we call it the Bernoulli equation when it is a special case of conservation energy equation that has the potential energy term, the pressure term, and the kinetic energy term on each side. That's the Bernoulli equation.